I'm Brian, I'm with Breker Verification, and today we're going to be talking about RISC-V vectors, their relationship to machine learning, applications, some common implementation, and crucially, their verification. So we've got a lot to get through. We're going to go pretty fast. We're going to start with some motivation. We're going to get to kind of a breadth-first search overview of RISC-V vector. We're going to look at some common implementation features, then look at an example test plan, and then we'll have a payoff with a test case. So to start, most of us are pretty aware of why this is such a big conversation right now. LLMs are, everyone's favorite universal paperclip these days, and it uses a lot of data. Training sets are trending towards the petabytes, which could take, with some back-of-the-napkin math, just 1 petabyte, 2 years to process on a normal scalar processor. So we must do better. One of the items of Flynn's taxonomy comes along to save the day. One of the components to solve this is SIMD, single instruction, multiple data. And so you can see kind of the basic idea here. Rather than each register representing one value, we can split that up into multiple values and operate on them in parallel. And here we've just split up a 32-bit register into several bytes, but with RISC-V vector, we can do much, much better, and you'll see the registers get quite massive. And here's an example of how that parallelization can work. All these similarly colored nodes in this neural network are doing the same calculation. You can split them out parallel, and you can get some really good speed-ups. And so this is some good data from ETH Zurich with their ARA. I think this was actually ARA 2. And you can see as they increase the number of parallel agents, which in their case are lanes, we increase the performance quite a lot. So now, what is RISC-V vector? So first off, it's very, very large. It's 32 vector registers, 7 CSRs, and about 200 instructions, depending on how you count them. So a couple of ground setting, just so that everyone's on the same terms of how these things work. Vector registers are that capital VLEN wide. It means vector length. It's not the best name because it overlaps with another name, but just keep in mind the capital VLEN, that's how long each vector register is. Those vector registers then get subdivided into elements. The size of those elements is determined by, among other things, your CSR state, which the 3 most relevant settings are your VL, another vector length. Now you see why I say it's a bad name. SEW, which is standard element width. That's how wide is each individual element. And then LMOL, which is kind of a grouping configuration. It lets you take multiple of these vector registers and operate them on them at the same time. So instead of just V0 plus V1, you could do V0 and V1 plus V2 and V3, and so on. It goes up all the way up to 8 at a time. So what does this get us? Well, one of the really, really cool things in RISC-V vector is that we have algorithmic scalability. So VLEN, that capital VLEN, is an architecture-specific parameter, which means that every architecture is going to have a different one. Does that mean that you can only write software for one architecture? No. Very cool thing is we have this VL max parameter, which is determined, you can see there, between that capital VLEN and the standard element width that you're using and the multiplier that you're using. And it lets us take, with the same code, and operate on different numbers of elements depending on what the architecture supports. So if your VLEN in this case was 128, you'd be operating on 16 elements. If it's instead 2048, you'd be operating on 256 elements at a time. So well-written software can be reused regardless of what architecture you're on. So what kind of things can vector registers do? And specifically, what things can determine what elements of what registers are going where? Easiest case, it can all be encoded in the instruction. This will always load one vector register with data. It can be encoded in that vector type. That's those CSRs. So the number of elements and the size of those elements that are added together depends on what values we put in those CSRs. They can be read from a source X register. This is a strided load. So this is going to take its data from memory. It has a base address, and then it's going to step up from that base address based on a stride, set, and X register. It can be from a source vector register. This is an indexed load. And so it does the same thing, base address, but then for every single element, you can have a different size that you're stepping. It can be encoded in all of the above. This is a segmented, index load, and you can see there's those dimensions in the end of it. Those are determining what the size of the indexes are. And then before that, we also get the number of fields, and then we still have the CSR elements. And actually, this encodes 2 different dimensions in the same instruction. That's going to come back. It can be determined from element-wise operations on multiple source vector registers, and we kind of get into Looney Tunes land here, where we get some very, very convoluted setups. I mean, this VRGather VV is kind of notorious for this. If you look at that equation over there, that's a double data dependency. So the elements that we're putting in VD depend on the elements of VS2 at the index of the data in VS1 at the element that we're looking at, conditionally depending on whether that VS1 data is greater than VL max. You can see why this gets complicated. And if you want to read that, go ahead and your eyes may glaze over. But we also have left out, all of these can also be affected by a mask and a tail. A mask is a set of, is a vector register. It's V0 is the one that you can use. And it's handled bitwise instead of bytewise, which also is going to come back. And tail, and then these can determine whether elements are operated on at all, whether they're always set to 1, which is that one of the options of the agnostic, whether they're ignored. And don't think that we're done with different types of control schemes. This one actually has a different set of indices. That's that VRGather EI16. The dimensions of the indices are determined by effective element width instead of standard element width, which means that all of these calculations have to happen. And then we also still have that conditional to deal with. And we have to even choose valid vector registers. We have to take into account all of these different dimensions for all of the different source and destination vector registers and make sure that they don't overlap depending on which instruction. All of that to say, there's a lot. It gets complicated. And the cross-coverage space of ensuring that you've exercised every possible element, every possible dimension, it's enormous. And unless you have some special approaches, which we're going to get into, it's going to be too much to deal with. So what are some basic implementation features? This is just so that we can see what our real motivations are here. This is from a verification standpoint. We have parallel lanes, which means that elements are getting shifted into different parallel units. I've used lanes in this case, but they don't have to be lanes. But basically what you should think of is that adds rigidity to the system. It's hard to move the elements between these lanes, or at least it's a thing that you have to do when you change your dimensions. Shifting could be a ring, could be other hardware, but basically you have to be able to move elements through these. There's specific instructions that do this, and also you have to be able to handle it when you change dimensions again. Mask handling, and specifically I want you to remember that vector registers can switch between being masks and non-mask registers, which means that sometimes they're handled as individual bits, sometimes they're handled as bytes, sometimes they're handled as words, and so on and so on. That adds a lot of difficulty handling, especially if you're reusing your vector registers. And then don't forget that it's also a load store unit involved, and that opens up the door to all kinds of coherency shenanigans. So how do we tackle this enormous space? Well, what you're looking at here on the right is our implementation of the abstracted test plan. So we look at it as a big graph. You can see each vector instruction gets its own node on that graph, and then they're connected by those highlighted lines to the different degrees of freedom that that instruction can observe. So different elmols, different standard element widths, whether it has a mask or a non-mask. These are all the possibilities in our graph. So if you expand those out, the get elmol has all the different options here. Your vector lengths, your number of fields, your standard element width. There's many more of these. They all expand out like this. They have all the degrees of freedom separated out so that we can constrain the graph at any time to pick any one of these options. Now, once we've decided all of our dimensions, we have to pick valid memories. That memory, keep in mind, we want to be reusing as much as possible to really make that coherency a difficult problem. And so you can see the other thing to consider here is that vector registers require enormous amounts of memory to test, because in order to have valid indices for your load, store, indexed operations, you need to have very specific sets of data to load into your vector registers. And that's many, many bytes of specific data pointing at specific addresses. Then we choose our vector registers that we want to operate on. There are some special cases that you have to consider based on not letting certain groups overlap with each other. But we also want to consider trying to reuse as much as possible and make the pipeline suffer. And then sometimes you want to do the opposite to try to get maximum performance. These are all options, and you can see them all split out there. Then once we defined all the, there's a little bit of some of the words got messed up here, but basically what I want you to see here is that we're initializing all of the different factors we've talked about, and then we have the vector instruction that we were targeting. What does this get us? So separating out in this graph seems all well and good, but what is the actual core reason that we want to do this? And I'm going to make the argument that coverage is a necessity here and is a very difficult problem to tackle. And so when we have our graph set out like this, every path along that graph becomes a cover point. And you can see here, we've given an example of how that can be unrolled. And you see these green ones have been exercised, the red ones have not. And each of these are a different combination of dimensions and other sequences, reuse, all of those things are all encoded in this graph. So you can get a real idea of what you've hit, what you haven't hit, and then constrain your future generation in order to hit what you were missing. And then our payoff for all of the effort we just went through. Here's an example test case. We can see some of the factors we were talking about over in the bottom right. Here's our assembly code, and this is just a snippet of it, but you can see we're changing our dimensions constantly to try to exercise those lanes. We're reusing the vector registers as much as possible, along with X registers and other things. We're adding a lot of cache line pressure based on the addresses that we're picking. And there's that memory map again that we showed at the top there. I mean, it looks a little bit like someone just scribbles on it because vector registers are so massive. But and then we also can split out into multiple threads that's both hardware and software threads. In this case, 2 software threads, 1 hardware, and they're running cotangent with each other. And then we have the nice pass-fail log down at the bottom here. So that's what I have for you. Thank you so much for listening.